All right, today we will learn about the multi-threading and synchronization. And then this is a transition from virtualization to concurrency. And then the important thing is that the Lab 3 due is approaching. So that's on the next Monday. So please finish Lab 3 as soon as possible. But you will still have like the 75 due date for the next week. So even if you cannot finish the Lab 3 on November 7th, please work hard on to finish that, because like you cannot work on Lab 4 unless you finish Lab 3. And then from the calendar, you are seeing there's a quiz 2 on next week. So quiz 2 is scheduled on Thursday and Friday. So like there will be 2-day window opening on the morning, and then it will close on the Friday midnight. Yeah. And then like it will have same unlimited time, and then you can have like up to 3 trials, and then I will just take the highest score. Yeah. And then, yes, question? All right, then I can do that. How about that? Like I can open that from Wednesday until Friday midnight. So if someone wants to use the holiday to like study about JAWS, yeah, I don't recommend that. So holiday is holiday. Please enjoy your time. But you can use that time for like for third trial to get the max out the kids score. Yeah, would that be okay for you? Yeah, right. Right, then I will make sure to open that on Wednesday morning, then open that up to Friday midnight. So, and then there will be no class on Tuesday. And on Tuesday, I will release the video for quiz 2 preparation. And then the quiz 2 prep video will be a little different than the quiz 1 prep video. So the quiz 1 prep video was like going over this very similar question one and over, and then like you can easily find the answer from those slides. But for quiz 2, I will not do that, but I will provide enough information that you can study about the virtualization part. Yeah. And then if you follow the slides or others during taking the quiz, you can definitely find the answer. That's the thing. So like there will be no in-person class next week. So on Tuesday, I will release the video for quiz 2 prep. And then starting from Wednesday, the quiz 2 will be opening. So like you can take the quiz during the class time or any other time that you are available. Any questions for quiz 2 and lab 3? All right, then I will move on to the content for today. So today we will have a transition from learning about the virtualization, about the isolating the process environment, and also setting up the virtual memory, those kind of stuff. So we have learned for those kind of thing for several weeks. And then now we will start learning about the concurrency part of the operating system. And the concurrency includes like the understanding the concept of the process and thread and how they are different to each other. And also we will learn more about how we can synchronize them while we are running the multiple thread and the multiple processes are each other. And then we will learn about how an operating system provides the primitives to application can organize that correctly. And also at the end, we will learn about like some of the misuse of the concurrency handling primitives may cause deadlock. So stopping the CPU and the operating system for indefinitely. And then we should avoid that. And we will learn more about those kind of stuff. And then like these contents are not covering only in today, so that we will learn those kind of stuff in several weeks. And then today we will start that kind of the concurrency part, and then we will learn basics of the process thread and then synchronization problem for today. So we will learn today. We will learn about like why concurrency is important and useful, and then the difference between the process and thread. And then we will take a look at the data racing case, and then we will learn about the concept of the mutual exclusion for synchronizing multiple threads. Then let's start with the why concurrency is useful and important in this area. So On the right side, I just put a graph, the data graph for like how the CPUs, microprocessors, were developed for recent 40 years. Yeah. And then you can see that the y-axis is exponential scale. So the year increased the 1 by 1, and then y-axis is increases 10 times per each block. So number of transistors stored in the CPU is increasing somewhat linearly in this graph. That means like the transistor numbers are increasing exponentially in the CPU. So 5 years ago, and then from now, we have a 10 times more transistors are getting into the CPU. So that's how the modern CPUs are keep evolving. And then have you heard about the Moore's law? Yeah. So from the CPU manufacturing company, Intel, there is a founder, his name is Gordon Moore, and then one of the founder. And then like he announced in like their early 90s or something, that the Moore's law is like in every 2 years or like the 1.5 year or something, the number of transistors can get into the CPU will be doubled. So that means like the projection of the semiconductor industry that like they will increase the performance of the CPU for 2 times, double the performance of the CPU in every 18 months or 2 years, that kind of time frame. And then that actually worked well. So you can see that this kind of the linear graph of the frequency of the CPU. So number of transistors can represent like the amount of the computing units in the CPU, and then how complex logic we can implement in the CPU. But actually what determines the speed of the CPU for this single thread, for just running the one program on the CPU, that actually determined by the frequency, because all the digital circuits in these days, they will have a base clock that alternates between 1 and 0. And then whenever the semiconductor circuits detects that 0 changes to 1, then they act something. So all the circuits are synchronized with the clock, and then you can think it as a clock as a minimal time that you can observe in the CPU. And then, for example, addition operation takes a 1 cycle in the CPU. So for example, if the CPU has 4 gigahertz frequency, then we can have like a 4 billion addition have executed on the CPU. For another example could be like the division operation is taking much longer than addition. So I'm not sure about the exact number, but it may take 3 cycles or something. Then we should wait until 3 cycles. But the 3 cycles in a 1 gigahertz CPU is around 3 nanoseconds. But the 3 cycles in 4 gigahertz CPU could be less than 1 nanosecond, right? So that defines like how long the CPU takes the time for like running the thing, so that we can easily guess like the higher frequency means that the CPU can run much more faster. But the interesting point here is that while the number of transistors in the CPU increase linearly in this graph, means that like that actually increases exponentially, but we are seeing that the frequency of the CPU is getting down recent years. Can you guess why that would be the reason? What will be the reason for that? Yes. So why will we have that kind of the cap for the frequency? So actually, we can make the chip size bigger and bigger by putting more transistors. And then another thing is like have you ever heard about the semiconductor process about the 10 nanometers, 7 nanometers, that kind of thing? So that actually defines the length of the transistors. And then if you shrink down the transistor size to like as a half, for example, from 10 nanometer to 5 nanometers, that actually gives the 4 times of the space because it's in a square. So like the 2 times the shrink, a half shrink on the like the width and height, then like it'll be like they're having like 4 times more space for that. So the chip size and the number of transistor is not a problem at all. But the problem is that I will write one of the equation on the board, and then I will share that to the Zoom side too. So I'm not an EE major, but one of the equation that holds for the like a semiconductor power consumption is that so C here means just a constant, and then F is the frequency, and then V is the voltage. Yeah, and then the power that the CPU would consume will be linearly increasing if we increase the frequency, and then quadratically increasing if we increase the voltage. And how we use that kind of a clock, and then how we use the digital circuit is that like in the nature, the values are not 1 and 0. So even if we would like to observe a clock as like the 0 and 1 and 0 and 1, how it actually works is like it is a smooth graph, something like this. And then we need to set the threshold. For example, if the value is like a 0.7, then that's definitely like if we have like the values from 1 and 0, suppose the observed value is a 0.7, then we may regard that as 1 because it's definitely over like a 0.5. Yeah. So like we will not get the exactly the value 1 for the like the having the digital value 1 for that. So it's something like there's some of the dead zones, and then if the voltage goes up above above the threshold, then we regard that as 1, and then if that goes down above the lowest threshold, then we will regard that as a 0. And the problem is that if we alternate the clock so fast, for example, right, nowadays we have a 4 gigahertz CPU everywhere, but if we increase that to 8 gigahertz, then even if we set the voltage from 0 to 1, it does not go up to 1, and then because it's changing too fast, so it could not be hitting the threshold well, and we cannot detect the 0 and 1 correctly. And then in that case, one of the solutions is that we can increase voltage range. Then that could have more buffer for like the accommodating that kind of the alternating thing, and then we can also have like a bigger range for the threshold dead zone kind of thing, so that would make the clock cycle much more stable. But the problem is that will increase voltage, and then voltage contributes to the power as a quadratic equation. So increasing voltage for 2 times means that we will consume 4 times more power. And then we will also increase frequency for that. So the logic is like if we want to increase the frequency, we also need to increase the voltage. And then that actually contributes as something like a cubic of the factor for the power. And then nowadays, like some of the desktop gaming CPUs that has like 10 cores, more than that, yeah, that uses 125 watts of the power. And then if we increase the clock for 2 times more faster, then like that may increase the entire power consumption for 8 times or something, then you will see that your CPU would consume like 1,000 watt. Maybe you can use like a multiple CPUs as a sum of the iron kind of thing. Yeah. So that might happen. And then our semiconductors are not that strong, like they can support like that kind of the 1,000 watt power on it. So the important implication is that there is a certain limit, that practical limit about the power consumption and so on, so that we cannot increase the clock cycle indefinitely. So there's a cap about like we can increase the frequency, and then that limits the single thread CPU performance. And then even if the Moore's law holds, they can put more transistors on it, but that they cannot increase the frequency. So if we cannot increase the clock frequency, then how can we get the better performance? So the answer is very easy. So we have more space for putting the transistors. So what CPU vendors are doing is like they're putting more cores on it. So I believe like the first time I saw about like a dual core CPU for the regular desktop consumer laptop use was in 2006 or something, so-called the 2005 or something. Yeah, Pentium D. But before that year, like the older desktop CPUs are running with the single core. Yeah. And then this is the diagram of the CPU circuit die. And then like if you open this kind of the CPU heat sink, then you will see a very small, like the size of like this one. So on the opposite side, there's a lot of transistors are condensed in in the die. And then that actually composed like this. So this CPU has 8 cores in it. And then it also has like the Intel has an integrated GPU and then memory bus, and then those kind of things are implemented in there. And you can easily see that the 8-core CPUs for laptop, because the laptop I'm using for teaching, this MacBook Pro, is equipped with the Intel's 8-core CPU. So that's quite a commodity in this era. And then another interesting thing is like the AMD developed another CPU called the Threadripper. And then what they have done was, so this is the diagram of each of like this chip die. And then it has 1, 2, 3, 4, 5, 6, 7, 8 cores in it. And then they put 4 dies of those chips and then connect each other. So it has 8 core, 4 times 32 cores in a single CPU chip. Yeah. And then because it supports splitting the 1 core as 2 logical cores. So if I run the Linux and then run the HTOP for the system monitor on it, then we can easily see like the 64 cores available on the system. So I just want to demonstrate like it's quite popular, and then like the trend in the computer systems are like putting more cores and then running more processes, more applications to speed up the execution. So the motivation for having a concurrency, running multiple applications in the operating system, is that the trend in CPU development is that like we have a cap in the clock frequency. Yeah. So these days, like recently, Intel released a new 13th generation CPU, and then it was rumored to have like a 6 gigahertz for the frequency. It's quite fast. But the problem is like we cannot increase it indefinitely. Like maybe in 10 years, could we see 10 gigahertz CPU? I don't think so. That's the problem. So to increase the system performance, because the number of transistors that we can put on the chip is keep increasing. So the easy way to do that is like put more cores on it. Yeah. So basically, because we have more cores on the CPU, and as a software, we can use them. We can use them efficiently to finish job quickly. So for example, if you have a long job taking 10 seconds with the single thread, then you might be finishing in 1 second with the 10 processes or 10 thread. So that's basically the logic. So it's something like if you work alone, it would take long. Then let's work together to finish the job quickly. And the modern operating system supports 2 options for having concurrency on the operating systems. So one way to have that is like running multiple processes. And then I draw the diagrams for the processor like this, and then you can regard that the gear icon is as indicating the CPU is executing that process. And then you can regard this green area is for the virtual memory space per each process. So the important thing here is that each core runs a different process, and then their memory space is completely isolated. On the other hand, for the thread, operating system gives another way to run the multiple CPUs in a shared virtual memory space. So in this diagram, 4 cores running on the same virtual memory space. It's something like if there's one process, and then we can put multiple cores run different jobs within the single process. And then today we will learn about what are the characteristics of the process and thread, and then we will compare and contrast about that. So let's start with the more familiar step, the process, because we have been dealing with the creating an environment in Lab 3. So that's actually matching to the concept of the process in the modern operating systems. For the process, so in creating the environment for Lab 3, the first thing we need to do is if we copy from the kernel page directory to create the new page directory, and then allocating memory by having a new page table for that specific process. So each process will have the isolated execution environment, and then isolated by the virtual memory space. So each of these processes will have different CR3 values, and then CR3 need to point to the page directory that it should refer to. So the CPU 0 is managing the process 0 page directory. CPU 1 goes to the process 1 page table, page directory, and so on. And that means that because they do have different page directory and page table, their memory spaces are completely isolated. Although they are residing all in linearly in the physical memory space, because CPU will regard all the addresses as a virtual after enabling paging. So there is no way that each process can directly access the physical memory, because the direct mapping is a kernel only. Yeah. So we can isolate each of the process, and then they cannot talk each other. But there are some of the cases that suppose there's one job, and then you split it into 10 instances and run it. But that there could be cases that each instances need to share the data each other for the collecting intermediate result or something like that. And to do that, because our memory space is completely isolated, we do need some of the mechanisms to talk each other. So although for the security purpose, we isolated each process, but that there are some needs that we need to make them talk each other in some managed way. And to do so, we can use some other mechanism to share the data. For example, each process can write a file, and then the other, as a result, then some other process can read the file written by the other process to share the data. That could be one of the case. And then the operating system internally provide several other mechanisms called pipe or socket or shared memory to share the data between the processes. So the things to memorize right now is that, so the process memory spaces are isolated, so we cannot access each other's memory. But to share the data, we need to use a different mechanism for sharing data between the processes. Any questions about the conceptual thing about the process? Right. Then let's take a look at how we create the new process, and then I will describe it in the context of JAWS. So this is the kernel page directory. You can regard it like that. So we have the kernel memory space, and then some other some of the data that we need to put on the virtual memory space, and then we have all the low memory as free. So remember that how we compose the memory layout in JAWS Lab 2. So we use like the sum of the address per the lower the kernel base, but there are like the U stack, kernel stack, and then those kind of thing. These are all placed on the upper memory of the virtual higher address of the virtual memory space, and then we emptied all the lower virtual memory space. And then whenever we call a env create, the kernel function that actually creates instantiates the process. And what we are doing is that we first duplicate the page directory and page tables of the kernel page directory. And then we allocate, so there are kernel page directory and tables, and then we duplicate entries of the kernel page directory. And then to allocate all these kind of the memory, we create a new page table to allocate that just for the processes the page directory. That will not be visible by the kernel page directory at all. Yeah. So the implication is that by creating new page directory and then having a private mapping to their own page tables, so the process will have the new private memory space. That's the thing. And then next, let's take a look at the if we run one program and then that program split itself by multiple instances and then running the job for like the parallelly running some of the jobs. And then we create from the kernel, we create the process memory from the kernel. And then you can regard this as a parent process that actually spawning multiple child processes to handle job parallelly. And then in Linux and other Unix systems, the system call called fork handles like the spawning a new child from a parent process. And then what we are doing when we run fork in the operating system. So fork is actually like the duplicating the current environment, current process, and then run the same code, but run different with the different data. Yeah, that's possible. And then to do that, we need to create the exact same instance to the parent, and then just to let them know you are a child, and then we can assign the different job for that. And what fork system call does is that it will just duplicating all the page table and directory, and then create a new process and then run it. So fork system call creates a new process by copying all the memory spaces, but it's actually dip copy. So there's a parent process page directory and page tables. And then to create the new child process, we duplicate page directory and then we duplicate the page tables. And then we also copy all the pages to the new physical memory and then assign that to the new process. And then I will explain about like the synchronization and then data share kind of thing based on this kind of the code snippet. And then let's follow the code. So in the C code, it will start from the main function. And then in the main function, what it will do is it runs fork. And then the semantic of the fork system call is that fork will return the PID, process ID of the child process if the execution environment is parent. And then fork will return 0 to the child process. So the reason is, so if the operating system runs fork, then one process will become the two identical process. Then there's a way that should be some of the indicator that we should know which one is parent and which one is child. And then that is done by the return value of the fork. And then after running fork, both process will continue to execute right next to the line. So when the parent process runs fork, one process will be splitting into two, and then both of them will run this count up function. And the inside of this countup function, what it does is like it will just keep increasing the counter one by one for 1 million times. And then it will increase the global variable counter. And then at the end, what it will do is it will check the PID. And then if that value is non-zero, that means it returned the PID process ID of the child, then it's parent. And then if that value is zero, then the child. And then it will just print out how many the count were increased by the parent. And then it will also print out how many counters increased by the child. So one of the questions from the Zoom side is like, did you mention the physical memory getting copied as well? Yes. So for a knife fork, we need to copy the page directory and page tables. And also we need to copy all the pages linked to the page table entry on the physical memory side to the new process, because we will regard the two processes are just independent one. So the sum of the counter updated from the parent should not be visible on the child side. And then the important thing here is that, so we have a global variable counter here, and then this countup function will increase that for 1 million times. But the problem is that these variables are not shared, because even the physical memory were copied, they will have a different physical memory to back this global variable counter. So the result is parent will count up until 1 million, child also count up until 1 million, and that's it. So the computation was done by the parent for increasing for 1 million times, and then child for increasing that 1 million times. So we might expect like a 2 million as the result, but that's not true. In the process, we have a completely isolated virtual memory. So even if we update on the counter on the parent side, that is not visible on the child side. That's the detail about the process. And then let's take a look at some of the good parts and the bad parts about the process design. So good thing about the process is that, so if the process has been built, what we need to do is just a fork and then run it. So that we don't need to change the application much, and then just fork and then run it. Then we can run like multiple instances of the same program. And then depending on like the child number, for example, we can run fork for 10 times. And then each time we create a new child, and then we can the number that as child 0 to child 10, and then assign 10 different jobs, and then write into the file. And then later parents can collect all the data from the file. So that's possible. But the bad thing is that the drawback of the process design is that if some of the data need to be shared, because the virtual memory is completely isolated, so we cannot easily share that. We have to use file pipe or some other mechanism for that. So we cannot directly access the data, so there must be some of the inter-process communications done there. So because of its characteristics, so processes are more suitable for parallel isolated execution. So we call like this kind of the job in the computer systems community as like some of the job is embarrassingly parallel. And then what that means is that like we don't have to do anything and then just create the multiple processes and then like assign each process to do this kind of job from here to there for one, here to there for the another one. Yeah, that's actually called embarrassingly parallel. For that kind of job, that does not require like the synchronizing the shared data in the middle or something. Yeah, that's suitable for like running parallelly in process. So the important thing is that the data sharing between the process is slow. So that's the important part. Then the question that immediately arises could be, can we have that kind of the multiple parallel executions, but at the same time, can we also share the data on the memory? The reason is like even if there's an inter-process communication exists, so that always need to go through the operating system. For example, if we open the file, the Ring 3 application do not have direct access to the disk. And then that should be mediated by the operating system, and then operating system handle that and then return it. And then that means like whenever each process want to share the data each other, they need to invoke system calls. And then like I didn't mention that before, but running a system call, it actually takes around 1,000 cycles, just changing the context from the user to kernel, because it need to read the trap frame and then all those things. So like so you actually see all the code, how what happens when the user level program invokes a system call. It goes to the trap entry, and then it will generate the software interrupt, IDT, and then do the old trap handling kind of stuff, and then get into the system call handler. So we need to execute a lot of instructions for that. But in contrast, if we share the memory space, we can share the data with single instruction. Just store the data to that thread memory. That's it. So that we could have like a 1,000 times more faster. Each the executions can share the data, and then that's why the thread kind of concept has been designed. So you can think it as thread is, it allows multiple CPUs running in the same virtual memory space. So that you can think it as, we are actually creating 4 different processes, but all these processes will have the same CR3 value. So for CPU 0, we put the CR3 value as this page directory. For the CPU 1, we also set the same CR3 value, this page directory, to CPU 1, and 2 and 3. Then all the CPUs will refer to the same page directory and table. That means they are running in the same memory space. And then if one of them update the data, then that can be visible to all the other CPUs. Yeah. So the biggest difference between the process and thread is that when we are creating the new process, we create a new page directory and page table to give a private memory space to the process. But for the thread creation, we don't do that. We just put another CPU, but assign the same page directory and table and just run it. And because thread design shares entire memory space, they can freely access any kind of variable. And then if one of the CPU updates that, and then that's visible to all other threads. That's the biggest difference between the process and thread. Then, how can we share memory space among multiple threads? So process creation is done by fork, and then naive design of the fork is that we need to copy page directory and page table, and we also need to copy all the physical pages and then assign to the new process. And then we have learned about the copy on write fork conceptually in the last lecture. So in that case, if we don't copy all the physical memory and making all the things read-only in the page table, and then map to the same physical memory, but whenever write happens on the page, we actually copy and then assign that to the process privately. So the important thing is no matter how we do fork, conceptually, the operating system design prevents sharing data among the process, and then the address space is completely isolated. But the thread creation is totally different. What it does is get a new execution environment. That means assigning a new CPU, another CPU to the process. And then what they are doing is, instead of creating new page directory and table, we assign the same page directory, just the same value of the CR3 of the original CPU that runs the thread. And then if we completely copy if we just assign the same memory page directory and table, then 2 CPU will run at the same point. But that's not what we want to do. So if there's a main thread, if it spawns a multiple threads, then we want each thread to do some of the parallel job differently. And then to do that, to distinguish one of the thread from the other, we create a new stack for that specific thread. So the difference is that in process creation, we need to copy the entire memory space. And in thread creation, we don't need to copy. We just assign the same page directory, but we will need to assign at least one physical page per each thread. And then that's for like a stack for the each thread. And then in the processes and threads, we use a stack for storing the local variables and then how the function calls are going on. So that kind of the execution context, it will be stored in the stack. And then to give the different execution context, even if we are running all in the same memory space, to give the different context, so we assign the different stack to each of the thread. And then let's take a look at the how it actually works in the diagram. So you can regard this as the one process running the main thread. So that you can regard that at this time, we only have one thread running in this process. So they are running with this U stack, so user stack, and then that will manage how the program execution goes on. And to create a thread, we can use the API called the pthread create in the Unix operating system. And then what it does is, so I marked that most of the lines as a dotted line, and then also like I made like the colors little whitish. The reason for doing that is like these are not actually copied. So what we do is like we just assign new process. So this is the new child thread is actually a process, and then we will assign the same CR3 value. So we don't copy the most of the part of the parent process, but we just create. So this is not dotted. So we only assign allocated new user stack for the child thread. That's it. Then after creating this and then let it run, so parent, while the parent runs with the user stack, the child thread will run on the user stack too. And then if the parent creates another thread, then they will create another user stack 3 and user stack 4. And then that's how like we can distinguish each thread from the others. Then let's go back to the same example. So I changed the code a little bit, but what it does is like from the main. So after creating the process, it will run the pthread create, so that it will create the new thread running the countup function. Yeah. And then for the countup function, we will, so the pthread create, it will create a new thread and then directly run this function. And then how it is being done is like when the parent process creates a new thread, so it will put this user stack 2, and then it will put the relevant information in the user stack. And then set the execution point directly to the countup, and then set its argument as a null. So null is 0. So for the child thread, it will have the argument value as 0. So that's why we can distinguish parent and child from that variable, because the argument value will be 0 for child. And then for the parent process, we will just run countup with 1. So the parent will have the value 1. So that's how we can distinguish parent and child, even if we spawn a new thread on the same memory space. And then this kind of value will never collide because they are stored in the different stack. And then after running this, child thread will run countup, and then parent thread will run the countup too. And then this countup logic is the same. So what it will do is like it will increase the counter by 1 for 1 million times. So we are expecting that the child thread count up for 1 million times, and then parent thread count up for 1 million times, expecting that they're having a 2 million as a result. But yeah, so the child thread will keep increasing the value. And then because this global counter is not copied, so it is being shared between two threads. So if the child thread increase the counter, then that will be visible to the parent thread. Vice versa. So if the parent thread increases the counter, then it will be visible on the child side. So the memory is completely shared. It does not require a system call, IPC, that kind of the inter-process communication for like sharing the values. It's fast and it's good. And then let's take a look at some of the good things and bad things about the thread. So the good things about the thread is that like it shares the entire memory space to share the data between the threads. We don't need to call inter-process communication. So it just need a one cycle if the data is cached in the cache memory, or like it just need like the 100 or 200 cycles to wait for the memory delay. But that's much like lower than the 1000 cycles or more than that for like waiting for the system call. And another thing is that whenever we create the new process with fork, we need to copy a lot. Page directory, tables, and then physical memory. In thread, we use less memory because in creating new thread, we don't copy the page, table, and directory. We just assign the same TRCR3 value to point to the same page directory. We don't copy that. And then we don't even copy the physical memory. And then we just assign new stack. That's it. Yeah. But the downside of the using thread is that there's no isolated execution. So if one of the child thread doing something bad, then the entire thing will be screwed up because they are in the same memory space. So it's something like suppose you are running a program with multiple thread, and then suppose you are accepting program from everybody here. Then if I, as a hacker, write a bad program for this one thread, then that can manage to modify the entire memory space. So that could affect to another thread and the main thread execution. So that could be possible, while that's completely impossible in the process design, because process isolate the virtual memory completely. And then we have seen that like the security problems happens if we don't use virtual memory at all. So in the physical memory space, if we run two different programs, then one program can access to another program's data area, that's problematic. And then that problem still exists in the thread. So the use for the thread is it's more suitable for parallelizing the execution for each of the instances need to share the data in the middle of the computation. Yeah, because the sharing of the data was slow in process, so we can use thread for the fast data sharing. And then it's not suitable for having a private execution because one thread can screw up all the thing because they are in the same virtual memory space. And then thread gives the good mechanism for sharing the data, but it does not come without limitation. So there is a synchronization issue. And then to learn more about that, let's take a look at the result of this program. So this program starts with the main thread and then spawn another child thread, and then both thread count up to 1 million. But if I run once, the result is something like this. And then if I run the program at another time, result is something like this. So I never get 2 million as a result. And then even the result is inconsistent whenever I run the program. Can you guess why? Yes, that's right. So we are operating with this on the same variable called counter. And then because two of the threads are updating the same variable, and then there is some of the data race issue. And then let's take a look at the example of the data race issue in detail. So in the code, we, yes.
So you use that volatile keyword so it doesn't where the compiler does not.
Right. Okay. Yes. Otherwise, it will just put 1 million as counter and then that's it. Yeah. So the modern compilers are so smart. And then if there's no other execution can affect on the calculation of the counter, then it knows that we are adding the same value to there. Yeah. Then without the volatile keyword, it will just put counter equal 1 million and then remove the for loop and then all the others. That's why I put that volatile keyword in there. So the important thing to know that we are using one line of the code to add 1 to the counter variable. But the problem is that this one line of the code can be compiled into 4 different instructions of the assembly. So this is the assembly lines that compiles this, compile the result of the counter plus value. Value is 1 for now. And then take a look at what it does. So this is actually the address of the value. So the GDB indicates that this address is pointed by RIP relative is pointing to the value. So what it does is it loads the value to the EDX register. So semantically, I can rewrite this as a more human readable form. So we store the value into the EDX register. And the second line, the address points to the counter variable, and then we will get the counter value to the EAX register. So the first one is the loading value to EDX. Second one is the loading the counter to EAX. And then the third instruction is the adding EDX and EAX and then store the result into EAX. And then that's actually adding value and counter, addition operation. And then now we have the result in the EAX register, not the memory. So we need to put that back to the counter variable to write that into the memory. So it's something like we need to get the value, we need to get the counter, add it, and then put it back onto the memory. So this single addition could be resulting in the 4 different instructions. And then that's the reason that why we have a data race. And then the important point here is that the thread's execution result could be inconsistent if other thread can intervene while executing these 4 instructions. Then let's take a look at how that could happen in reality. So adding value to the counter, that could be compiled in these 4 instructions. And then we assume that the counter starts with 0 at the start, and then value is 1, and then we are keep increasing 1 by 1. And then suppose 2 threads are executing these 4 instructions, luckily independently like this. So you can regard that this is thread 1 and then thread 2, and then y-axis as a time. So that we are executing this and then thread 2 will execute the other of the instructions. So in that case, we can follow the instructions and how the counter values are updated. So first, EDX load the value is always 1, and then EAX load the counter value. Originally at the start, it's 0, and then counter plus value is 1, and then we put this value 1 back to the counter. And then later, if the thread 2 reads the data, value is always 1, counter will be 1, so that this value has been stored into the memory, and then the child thread fetches this memory to the register. And then we add up and then put the result back to the counter. So this will result in consistent result. But the problem is that our threads are completely parallel, so it does not run like this. What that means is that it could intervene the execution after running 3 instructions of the thread 1, and then thread 2 may running these kind of instructions. So one of the example is that, so suppose thread 1 executed these 3 instructions, and then suppose the operating system receives network device receives a lot of packet, and then that network device card generate the interrupt to the CPU 0 that runs thread, then it will be intervene the execution, and then it will move the execution to the kernel and then handle the network packet kind of thing. But at the same time, because thread 2 runs with a different CPU, then they can continue to run on the same job. So that this kind of the condition can happen. And then let's take a look at what will happen if the other execution that touches the same variable intervenes while the one thread is executing on it. So the same thing, load the value to EDX 1, load the counter to the EAX, the original value is 0, and then we add up to get the future counter value as 1. But before the thread 1 storing this value to the memory, so this EAX register is in CPU, so only the CPU 0 has the result. It has not been committed to the memory. Then the thread 2 starts execution. It gets value 1, and then it will get the value counter as a 0 because that variable has not been updated. Then, as a result, thread 2 will commit value 1 to the memory. And later, if the thread 0 comes back from the interrupt handling, then it will write the counter value as 1, not 2. So, because this write is not visible when the thread 2 loads the counter variable, it may result in an inconsistent result. And then we have seen that whenever I execute the same program again and again, I'm seeing the different result. The reason is I ran that program in running in an environment that the regular environment that runs multiple processes are running. So even in this laptop, around the 300 processes are running in there while we have 8 cores. So there are several cases that either of the thread got scheduled for the handling another process while the one thread is running. And then arbitrary interruption of that kind of execution may generate a lot of these kind of cases. That's why we are not updating each of the value, but that could be ignored in each of the thread execution. But not all intervention affect on the data race. So let's take a look at some other case. So suppose thread 1 have retired the 3 instructions, and then thread 2 executes the first 2 instructions and then got intervention, and then thread 1 commits the counter value. In that case, this counter value is not visible to the load of the child thread, so that it will result in the inconsistent result, right? So the important thing is that this load must happen after one of the thread that tries to update the counter finishes. Before this instruction finishes, if we run this loading up the counter instruction, then it may lead into the inconsistent result. So this load should happen after the writing of the memory from the thread that executed first. So if the intervention luckily hits on something like this, then thread 1 finishes the updating counter here, and then even if the thread 2 run the loading of the value first, have an intervention, the loading of the counter from the thread 2 happens after the thread 1 stores the value. So in that case, that value will be visible to the thread 2, so they can update counter value to the consistent to yield the consistent result. Yeah. So the problem is that like if we just run it, then there are many of the cases that we will face these kind of the data racing cases that yields into the inconsistent result. Yeah. Then what is the main reason for like having that kind of data race? So the root cause is that like there are many threads are running that, but while one thread is trying to updating the value, if that execution is intervened by the other thread execution, then the sum of the update that the thread running ahead of time update the value, that kind of value is not visible to the other thread. Yeah. So the important thing is that the store instructions of the thread that runs ahead of time, yeah, that should be finished before the loading of the instruction, loading of the data on the subsequent running of the thread. Yeah. And if we just run it, then like there could be many cases of like that kind of having that kind of data race. And to avoid that, we need to delay the execution, delay all the other thread execution to have the storing of the counter value of the thread must be finished before the new thread try to loading up the data. So conceptually, what we need to do is like whenever thread 1 tries to update the counter value, we need to stop the thread 2 from doing that. And then after the thread 1 finishes it, then we can continue the second thread. And then we call this kind of concept as a mutual exclusion in parallel execution. So the mutual exclusion is like usually combined with the concept called the critical section. And then what a critical section is that? So we have seen that like we could have like a multiple instructions for doing a single operation. And then we do not wish to have like any kind of the intervention of the execution happens from the other thread while we are executing all the instructions in there. So the critical section here means that we define the region of the instructions from here to there, and then we would like to create the conceptual thing that while one of the threads are running inside of this critical section, if the other thread wants to run on the same critical section, then they have to wait. Yeah. So that's how we implement the mutual exclusion. And then as a result, we can make the only one thread can update the value at the same time. Okay. So even if the thread 2 wants to run the critical section, it cannot run before the first execution finishes. And then after the counter value store finishes and then the execution ends, then the other critical section can start. And by doing so, we will always make the store happens before the another thread fetch the value. And then this is how we can make the critical section execution. And then the order could be arbitrarily. So that maybe thread 2 execute first on the critical section. But if that happens, then we need to make the thread 1 should wait. So how it works is like whenever one thread comes into the critical section, before it exits, no other thread can execute on the critical section. So that's the thing. Any question about this critical section conceptually before getting into how we can actually implement that? All right, then I will move on to the implementation of the that kind of mutual exclusion. So one of the methods that we can create the mutual exclusion in a single core computer. So the reason why I'm mentioning that is the single core computer is that we cannot use this mechanism for multi-core, and also we definitely do not use this kind of mechanism in modern operating system. But we will just learn about like there's a mechanisms, something like this, but we should never use that. And then what we can do is, assuming a single processor environment, we can run CLI. That's a clear interrupt flag, so stopping any kind of interrupt. And then run 4 instructions, and then enable interrupt again. So what this means is that, so suppose thread 1 is running on this critical section, and then it will disable the interrupt. Then there's no way that interfere this execution. So the CPU will execute these 4 instructions without having any kind of interruption. And then we can turn on interrupt again. Then maybe later time interrupt comes in, then switch to another thread, and then that thread can update the data. But that's okay, because thread 1 have already updated the counter value. So conceptually, we can block any kind of interruption and then run all the 4 instructions and then enable that again. And then that's the one way that we can make the mutual exclusion happens. So because the reason why we do not use this kind of thing is that, so in a multi-core CPU, even if we disable the interrupt for the one CPU, another CPU runs completely independently, so that they could have an interrupt, and then if the other CPU runs a thread, then even if this CPU blocks the interrupt, the other execution can intervene inside of here. Yeah. And then another problem is that the CLI, STI, these only are available for the ring 0. So as a user level application, we cannot use these instructions. Whenever we run these instructions, then it will generate the general protection fault, because these instructions are only available for ring 0. So this is not the way that we are implementing the mutual exclusion. But instead of doing that, what we will do is we will implement the conceptually lock and unlock function. And then the characteristics of the lock function is that, so it will first check if any other thread running in a critical section. Then if there's another thread, then it waits. It's just having a while. If the lock variable is 1, then just keep waiting. And then if there's no other thread are running in there, then we can start executing that. And then once the one thread get into the execution by passing the lock, then they will execute up to the end of the instructions. And then after that, they will call the unlock function. And what unlock function does is like notifying the other thread that like that they can acquire the lock. Question? So there are different mechanisms that we have to use for like the assigning priority for the lock, but the basic lock does not have like the regard the priority for that. Yeah, but we will learn more about how we implement the lock in the next lecture, and then I will give the more detailed explanations about like how we can implement something more, yeah, to implement that kind of the priority-based feature. Yeah, because like right now I can describe that, but that's all like description in verbal. But what I think is like it'll be better to have like some of the implementations shown on the screen and then explain that later. Yeah. So we would like to implement this kind of the primitives, and then how we can do is it's very simple. So whenever our thread hits the execution of the lock, then we need to check if there's any other thread running, then we should wait. And then if there's no other thread is running, then we get into there. And then at the same time, we need to mark that I'm running on the critical section to prevent all the others are entering to the these instructions. And then after running this critical section, when we run unlock function, then we need to notify all the other thread about like that now you can get it. And then we will learn about how we can implement the log and unlock in the next lecture. But let's take a look at the how that may create the critical section. So suppose the thread 1 runs first, then we have a virtual critical section defined by lock and unlock. So the first instruction that we will run is like the lock function. And then because this thread has get into the critical section, no other thread can get into the critical section at all. So thread 1 will run the instructions. And then after thread 1 runs the first instruction, let's suppose the thread 2 would like to enter to the critical section. So that they will run the same lock, but this log execution knows that the other thread is running in the critical section. So it will wait until thread 1 finishes the execution and then call unlock. Then unlock will notify all the other thread about like they can acquire the lock. And then the first one acquires the lock, get into the critical section, and then runs these 4 instructions. But the same thing, after running no matter how many instructions at here, if the critical section has not finished it, but another execution wants to get into the critical section again, then they should wait until the thread acquire the lock, finishes the execution on the critical section and calling unlock. Then the other thread can run on there. So in this case, we are seeing that storing of the counter value always finish it before another thread load the counter value. Same thing happens, storing of the counter value of the one thread will be visible to the loading of the counter for the another thread. So that we can actually order the store and read in this kind of fashion by creating a critical section virtually using lock and unlock primitives. And then you might be curious about like why do we use this kind of the mutex? Because you may think it as like we are using mutex in the critical section for updating counters. And then if we run the thing, something like this, then while the thread 2 is running critical section, thread 1 cannot run it. While thread 1 running on the critical section, they cannot run it. So it's actually same as just running one thread for running 5 critical sections. So we don't have speed up in this case. Yeah. But yes. No. So in the middle of the critical section, if the thread 1 got interrupted, then thread 2 should wait. So the critical section means that the entire thing needs to be finished first to have another thread can execute on it. So that if the interrupt happens in the middle of the critical section, then no other thread can run it. So the important thing is that we cannot make the entire parallel job as a log and unlock critical section. So if we combine all the program as a log and unlock, then it's actually same as like the running program sequentially, serially with one process. Yeah. So to avoid that, what we usually do is, suppose there are parallel jobs, but not all jobs are requiring the shared variable updating. Yeah. So what we need to do is, so we use critical sections for the part that really require that kind of the mutual exclusion. So for the part that has like the updating of the shared variable. So we apply only to those parts. And then for the not relevant part for the updating the shared variable, we can leave it as like a non-critical section. Then the execution would be, so while the thread 1 is running like this, if the thread 2 runs these program, then while the thread 1 is running on the critical section, thread 2 cannot start. So they can do some kind of the other parallel job first, and then they can run on the critical section while the thread 1 is doing something else. Then in this case, if we run the entire program as a single thread, it requires this amount of time. But if we run it parallelly, then only the critical section part are serialized, but the other things are parallelized so that we can finish it in a short time. So I have 3 more slides, and then let me finish it in 2 minutes. Yeah. So the important thing here is that like we can use mutex, mutual exclusion, to synchronize the shared variable update, but we must use mutex only if it is required. Otherwise, it will result, if we set the log and unlock for the entire parallel job, then it will result in like running in the serial, running in the single CPU would be better. Yeah. So parallelism would be meaningless. So like the making the critical section shortest enough, yeah, it would be the key factor for like the having a performance in this kind of the execution. And then in coming lectures, we will learn about like how we can implement that kind of lock. And then I would like to show like one of the naive implementation of the lock. So this is a bad lock and bad unlock. And then what bad lock does is that like there's a lock variable, and then the value of the lock variable initially will be 0. So what lock function does is that whenever a thread get into the critical section, lock variable will become 1. So if that value is 1, it will keep waiting in the while loop. And then once the lock variable value becomes 0, then it enters to here, and then immediately it will update the lock variable as 1 to make all the other thread waiting at here. And then unlock, for the unlock function, we can make it as setting the lock variable as 0. Then to let the others can break while and then get into the critical section. And then by using this bad lock and bad unlock, so we can wrap the count up instruction, count up line with these 2 primitives to create a critical section. Then the execution would be, so it runs bad lock, and then originally the lock variable was 0, then break the while loop, and then set the lock variable as 1. And then running these kind of the instructions, but at that time, suppose the thread 2 gets in, then because the lock variable is 1, they should stay in the while loop. And then after the thread 1 finishes the execution, updating the counter, and then if they call bad unlock, then the lock variable will become 0. Then thread 2 can break from the while, and then immediately it will set the lock variable as 1, and then continue to execute. And then it will do unlock, then to let another thread get into the critical section. So that this is one of the way we can create the critical section, but you can have a conjecture that from the name, bad lock, bad unlock, it does not work consistently. Yeah. So we will learn more about like how we can implement the good lock and good unlock, and then making it more performant in next lecture. And then to give another hint, this kind of mechanism only works in the single thread CPU, a single core CPU, but in a multi-core CPU environment, it does not work. And then the final summary about what we learned for today. So Important thing is that we have a cap on the single thread CPU speed, so we cannot increase the frequency indefinitely. But the good thing is like the Moore's law still holds. We can put more transistors, so we can enjoy like the multiple cores are available in desktop laptop CPU for now. And then the operating system provides like two ways of like exploiting the concurrency. So one is process and the other is thread. And the biggest difference is that the process has a separated, isolated virtual memory space, while the thread shares the entire memory space to have like a better like the data sharing between threads. But the problem is that the thread may have the data racing, and then to resolve the kind of the data racing, we can create the lock and unlock primitives to create the critical section to have a mutual execution on the data sharing part. All right, this is the end of the lecture today, and thank you for your attention. And then feel free to ask any questions.